This is the last section in Unit 2A, Section 2.5. We'll be talking about the characteristics of acids and bases and how we use indicators and the pH scale to determine if a solution is acidic, basic, or neutral. So let's talk about some characteristics that differentiate acids from bases. We learned in the last section that acids produce the hydronium ion in water. Remember, it is really the hydrogen ion that is released from the acid molecule when dissolved in water and automatically connects with the water to form that hydronium ion. Now, we don't taste acids in laboratory, but there are some foods that have weak dilute forms of acids in them, and those generally taste sour. We've learned that active metals can react with acids to form hydrogen gas, and you can see in this chemical reaction right here the active metal being magnesium and the production of hydrogen gas on the right. And the last thing is that an acid, we'll use that same acid, hydrochloric acid, neutralizes a base, we'll use sodium hydroxide, and it always forms water and a salt. In this particular case, it forms sodium chloride, which is table salt, but a salt is really an ionic compound, any ionic compound that is formed when an acid and a base react with one another. On the other hand, we've got bases, and we learned that they produce hydroxide ions when dissolved in water. Under the same circumstances as before, weak dilute bases will taste bitter, they feel slippery, and they will also neutralize an acid to form salt and water. We could use the same example we just did over there. What they both have in common is that when dissolved in water, they form ions, and it is those ions, those free-moving charges, that conduct electricity. So both acids and bases are called electrolytes. So this is just a snapshot of some common household acids and bases. You can see on the left we've got lemon juice, vitamin C, which is ascorbic acid, and looks like baking powder. On the right we have bases such as Drano, baking soda, oven cleaner, ammonia, and so forth. We need to talk about the difference between strength and concentration. A lot of students get these two words mixed up. Let's start with strength. We're going to be looking at the terms strong versus weak. An acid is considered strong when all of the acid molecules separate into hydrogen ions when dissolved in waters. Another word to use for separation is dissociation. So when we have only ions present, because all the acid molecules have dissociated, it's considered strong, like you see in examples below of hydrochloric, nitric, and sulfuric. A weak acid is only going to have some of the molecules separating into hydrogen ions when dissolved in water. Very few ions will be present. Mostly molecules will stay together. Okay, so you have very little dissociation. Examples would be vinegar, which is basically acetic acid, and carbonic acid. If you take a look at this diagram, you'll notice that the acid molecule looks like this. And as it's being dispensed into the water, you can see that all the ions are separating from each other. And so you have the hydrogen and the anion component of the acid all apart from each other. So you see 100% dissociation here. On the other side of the diagram, you can see that same acid molecule going in, but this time you see that most of the molecules stay together, and only a few of the ions are separating from each other or dissociating. Thus you have a weak acid compared to a strong acid. We'd like to say that there's 100% dissociation here, somewhere between 1 to 5% dissociation here. Here's just another picture to show the difference between strong acids versus weak acids. On the left you can see that there are no intact acid molecules. They have all separated into ions. There's a complete dissociation here. Whereas on the right you can see that there are mostly molecules, acid molecules, intact with just a few ions floating around. So only slight dissociation. Now the other two terms we have to talk about is concentrated versus dilute. These terms refer to how much of a substance is being dissolved in the water. We're going to say that the solvent is the water and the acid molecule is the solute. So solutes get dissolved into solvents. The more solute we put in, the more concentrated it becomes. We say it has higher concentration. The less solute we put in, the more dilute it becomes, and thus the lower the concentration. So we're really looking at how much is getting dissolved here. We're not looking at how the molecules are separating from each other into ions. We're just looking at how much we put in originally. Now there's all kinds of combinations of concentration and strength. We'll start off by looking at the strong and concentrated. That would be where we have a lot of the acid or base being added, the solute, and all of the acid and base will dissociate, will split apart into ions. You can also have strong and dilute. That means that, once again, all that we add will dissociate, will split apart into ions, but this time we're not going to add very much in the beginning. We can have weak and concentrated, and that would give us a scenario where we're going to put a lot of acid or base into water, but only a little bit will dissociate. This is that 1 to 5% dissociation. And the last scenario would be weak and dilute. We're not adding very much acid or base, and that little that we do add, very little, will break apart into ions. So here's a visual of those 4 scenarios. We're going to start off by noticing that each one of these boxes contain hydrogen ions either by themselves or within the actual molecule. And so that tells us that in all 4 boxes we are looking at an acid. In this first example, you can see that there's really only one set of ions here. Everything else stays as an intact molecule. So this must be weak. And the fact that it's pretty crowded in that box means that it's concentrated as well. If we take a look at the second box, you can see that there are no intact molecules. All of the species present are ions, which means that this has to be a strong acid. And the fact that, once again, it's pretty crowded in here means that it's going to be concentrated. In the third box, you can see that mostly the intact molecule remains only one set of ions. So we know that this has to be a weak acid, and it's kind of sparse in here. It's not very crowded, so we're going to say that very little acid was actually dissolved in the water. So we're going to say it's dilute and weak. And in this last scenario, you can see that nothing but ions are present, which means it has to be strong. And it's not very crowded in there, so it has to be dilute. Not much solute has been added. 2 slides ago I mentioned bases when we were talking about the different scenarios of concentration versus strength. I just want to remind you that bases follow the same pattern as acids. A common misconception out there is that acids are more dangerous than bases, and that's simply not the case. I want you to know that the stronger an acid or base is, and the more concentrated it is, the more dangerous it is. So just to kind of give you 2 points of interest here, vinegar is an acid, acetic acid, and we use it in our foods, and it's perfectly safe. It's also a very weak acid, and we use it in dilute form. However, sodium hydroxide, okay, which is a base, is very caustic, and especially if it's concentrated, it can do a lot of danger to us. It is a strong base, and so that's what makes it very harmful to us. Now there is something called the pH scale, and that runs from 0 to 14. 7 is the neutral point, and anything less than 7 is considered acidic. Anything higher than 7 is considered basic or alkaline. The closer you get to the ends of this number line, the stronger the acid or the base become. So a pH of 2 is going to be stronger than a pH of 6. A pH of 13 is going to be stronger than a pH of 11. There are many ways to measure the acidity of a solution. pH happens to be one of them, and we have many indicators that can help us determine that as well. We do have liquid indicators, and the two that you're going to be using in class are phenolphthalein and bromothymol blue. And you will need to know that with the introduction of phenolphthalein to an acid, it would stay clear. So phenolphthalein is originally clear, you can see that here. And it would turn pink in the presence of a base, and that's what you see in this third slide right here. I'm not showing a picture of bromothymol blue, but when it's dropped into an acid, it turns yellow, and when dropped into a base, it turns blue. We also have pH meters or pH probes, which electronically determine the pH and give you a readout, and then you can actually use that number line to predict whether something is acidic or basic as well. Lastly, we have paper indicators, and the two paper indicators that we're going to be using are litmus paper and pH paper. So over here to the right, we have blue litmus paper and red litmus paper, and you can see that the red litmus paper is turning blue, and that usually signifies that the solution is a base. And here we see blue litmus paper turning red, and that will signal that we're looking at an acid. One of the things that I like to write on the board, and I will do it here, is this kind of mnemonic to help you remember that blue represents a base and red represents an acid. So if I originally start with blue litmus paper and it stays blue, it would be a base. If it turns red, it will be an acid. And sometimes we refer to the red as pink. If red litmus paper stays red, it's an acid, but if it turns blue like we see over here, then it would be considered a base. The other type of paper indicator we have is pH paper, and you would just tear off a segment of this paper, put it into the solution. It turns a color which matches to a pH number. So let's say we get this color, we know that's a pH of 3, and you can go back to your pH scale and determine that pH of 3 is acidic. This is a list of some common household substances and their corresponding pH value so that you can determine which substances are acidic, basic, or neutral. Notice that pure water is neutral, typical rainwater is slightly acidic, and cola is even more acidic with a pH value of 3. This concludes Unit 2A. We've done a lot of naming of compounds, a lot of formula writing, and that gets a little tedious. It's going to get a little bit more interesting as we move into the next section. We'll actually get into some chemistry, balancing equations and predicting reactions and so forth. In order to do that, you have to know how to write a chemical formula. So don't give up on this unit. Please practice as much as you can with your formula writing and your naming of compounds. And just remember about acids and bases, because we will come back at a later date and discuss them in more detail. Have a great day.